Hello, welcome to the second part of our lesson on the method of three-moment equation using it to analyze um, continuous beam. My name is Engineer Dr. Edidongi Ambrose from the Department of Civil Engineering, Kwebon State University. Please don't forget to subscribe to this channel if you have not done that before, so that whenever we post a video, you will be getting direct access to it. So we are going back to the second part where we stopped in the first part, and this is we are looking at example 2 now. Example 2 is similar to example 1. The difference is that there are three spans here. So we are told the question is analyze and draw the bending moment and shear force diagram of the beam beside, indicating maximum moment and shear forces. You have to take EI to be constant throughout the span. So we have two span here. First thing, note that this load, they are not at mid-span. They are not at mid-span. So there are two, point load here, UDL. So the first thing, remember in the method of three moments equation, we only work at two span at a time. That is three adjacent support. So what we are going to do, we are going to work on span AB and BC. When we finish, we now work on span BC and CD. So the next thing we are going to look at in this our beam, how many unknown support moment do we have? We have 1, 2, 3, 4 support moment. But because this is simply supported, we know that MA is 0. We know that MD is 0. So there are only two unknown support moment, which is MC, MP, and MC. So it tells us that we need two equations to solve for MB and MC. So we are going to use span AB and BC to derive one equation, and then we do BC, CD to derive another set of equations. So let's start by considering span AB and BC. We have these two spans. In this span, we have a point load that is not at mid-span. When you have a point load that is not at the mid-span, a point load, it will still give you you will still have a triangle kind of, but it's not going to be an isosceles triangle because the load is not at mid-span. Now, how to calculate that load is PAB over L, where this is P. A is a distance from this support to the span to the where the load. B is from where the load to the other support. So we do PAB over L. It might do you some favor to take note of all this formula they help. So PAB, that means 9 times 2 times 4. That gives us 12 kilonewton. Okay, PAB over L. 9 times 2 times 4 divided by L, and L is 6, so that gives us this 12 kilonewton meter. And the same thing here, PAB over L in this span, the load is not at mid-span, so you do PAB over L, and it gives us 9.6 kilonewton meter. Now, since this triangle is not an isosceles triangle, that means it is not symmetrical. You cannot just put the centroid at the mid-span, no. So we are going to split it into two right-angle triangles. So you can now. So when we split this into two right-angle triangles, the centroid of this first one, remember the centroid is 1/3 from this side and 2/3 from this side. And the centroidal distance we are looking at from the external support. So from here to here will be 4/3. It will be 2/3 of this distance. 2/3 of this distance. And this distance is what? Is 2. So 2/3 of 2 is 4/3. Now this one, when you have this centroid, the distance from this centroid to this place is going to be 1/3 of this distance. So 1/3 of 4. So you have 1/3 of 4. Now when you're taking the distance from here to here, it's going to be 1/3 of 4 plus 2 that we have here already. That's why we had 10/3 at the distance from here to here. So we come to this other side. We split the triangle into two. This triangle is 2 over 3 of this distance. From here to here is 2 over 3 of this distance, and that distance is what? 3. So 2 over 3 of 3 gives us 2. And from here to here will be 1 over 3 of this distance. 1 over 3 of 2 plus this distance, which is 3. So that gives us 11 over 3. So with that, we can go ahead and find our area. So if we come for 1, for this other part, the left support span AB. A is the area. A1, X1, that is the area and the central distance. So for each of these, we're going to multiply the area by the central distance. So we go, for this one is half, the area is half base times height, which is half. This is the base 2, this is the height. Multiply by what? X1, which is the central distance. Central distance is 4 over 3. So that's why we have this, the whole of this first bracket. The second bracket is this one, half base times height. What is the base from here to here? Okay, half here. The height is 12, which is this. The base is 4. The central distance is what? 10 over 3. So we want this 10 over 3. By the time we multiply the whole of this, we have 96. So we go to this second part and do the same. X2, A2, X2. If we do the same like we did to that one, we have the 64. Remember our L1 here, L1 is 6, our L2 is 5. So the final thing is to apply the 3-moment equation. By applying the 3-moment equation, we now write the 3-moment equation, which is this equation, and then we substitute our variables. Our MA is unknown. L1 is 6, so we have 6 MA. Now, L1 plus L2 is 11. That is 6 plus 5, 11 times 2, 22. So that is how we have this 22 MB. This is 6 MA, 22 MB. Now, MC, L2. MC is not known. L2 is what? 5. So we have 5 here. So this one, okay, I think they must have been here. This is 6 times, we know that A1 X1 is 96, so it's 6 times 96, and L1 here is 6. Now, this is A2 X2 is 64, 6 times that over L2, which is this. So the whole of this was sum up to have this minus 172.8. But we know that this is a simply supported beam. MA is 0. So we can now say since MA is 0, the whole of this component is gone. What we have left is 22 MB plus 5 MC equals to minus 172. Because we want to use the substitution method to solve a simultaneous equation, we make MC the subject of the formula. Since we know MC will appear in the first and second equation, we make MC the subject of the formula. So that gives us MC equals to minus 172.8 minus 22 MB all over 5. Let's call this equation 1. Okay, so the next one is to consider span BC-CD. If we come to span BC-CD, that is BC-CD. BC, we have a point load here acting on a midspan. CD, we have a UDL acting through the entire span. So we now come here. This is our span BC. We have a load. Remember how we had this 96, but the central distance will now change because we are now taking to support B, distance to the external support, which is support B. So for this one, here is going to be 2 over 3 of this distance, and this distance is, what was the distance? This distance is 2. So we are going to do 2 over 3 of 2. It gives us this. This one will be 1 over 3 of this distance. This distance is 3. 1 over 3 of 3 plus this distance, which is 2. So 1 over 3 of 3 is 1. Then plus this 2. So that gives us 3. So we go to this one. This one is just a semicircle of WL squared over 8. Remember, this is L3. WL squared over 8. So that gives us 6 kilonewton meter. And the center is just from halfway because this is a semicircle. So we just have halfway from which is 2 meters. So we now go ahead and calculate our A2x2. A2 is the area we have two components. So this one is half base times height, which is half the base times height multiplied by the central, which is this plus. For this one, no, for this other one, half base times height, which is half the base times height. The central distance is what? 3. So we have this component. If you work it out, it gives you 56. Now for this other one, A3x3, what is the area? This is a symmetrical. The area is 2 over 3 BC. 2 over 3, where B is this distance, which is for here is 4, and H is 6. So we have 2 over 3 times H6 and times B, the central, which is 4. The central distance is 2, so you multiply by 2. That gives you 82. Remember, our L2 is 5. Our L3 is 4 meter. You can go back here. This is 5 meter, this is 4 meter. So we write the three moment equation again in terms of MB and MC. So this is a three moment equation. If we substitute a value of our L2 is 5, so this is 5 MB. This place, this is 5 plus 4, which is 9. 9 times 2, 18. So okay, already first of all we put this is 5 MB, this is 2 MC into 5 plus 4, 4 MD, all equals to, we now substitute this value. But MD is 0. Of course, we know that MD is 0 because this place is simply supported. There is no moment there. So MD is 0. So that reduce, cancel this component. We now have 5 MB, which is this. This one, 5 plus 4 is 9 times 2, 18, 18 MC. We equated the whole of this, give us minus 115.2. So we can now make MC the subject of the formula again. So MC equals to minus 115.2 minus 5 MB all over 18. And so we can solve the simultaneous equation. You can use any other method to solve the simultaneous equation, but when I solved it, MB was minus 6.84, MC was minus 4.48. And in this method, if you do things right, the support moment will always be negative form. Support moments are considered negative using our sign convention. So having done that, we have found our moment. So we can now come here. This is a MB, which is 6.84. This direction shows it is anti-clockwise. It is an anti-clockwise moment of what? 4.48 kilonewton meter. I'm going to use that method again to find our support reactions. In this case, if we stand at support B, we stand at point B, and we know the bending moment to be 6.484. So we take bending moment by the left hand side. So bending moment can be to the left hand side. So if we do that, VA will give us a clockwise moment. So it's going to be positive, and the perpendicular distance is 6. So that's why we have 6 VA. This load is going to give us an anti-clockwise moment, which makes it negative. The perpendicular distance is 4 from B, so we have minus 9 times 4. There is no other force except VB. This VB, if you take moment, is going to be 0 because the perpendicular distance is 0. So we equate it to this moment, minus 6.84. We solve for VA. VA gives us this. We stand at point C. We take bending moment to the right because we have only one unknown VD we want to solve. So if we stand here, take moment to the right. Remember, whenever we are taking bending moment to the right, the sign convention will reverse. So in that case, the first force is VD. VD is producing an anti-clockwise moment, and in this our new sign convention, anti-clockwise moment will be positive. So you have VD. The perpendicular distance between VD and C, where you're taking the bending moment, is 4. So that's why we have 4 VD. 4 VD. And then the next thing will be for us to take the moment due to the 3 kilonewton UDL. So the UDL will make a clockwise moment. So in this our new sign convention, clockwise moment is negative. So that's why we have minus 3, the magnitude of the UDL multiplied by the length of the UL, which is 4. And it will be acting halfway, which is 2 meters from where we are taking moment. So that's why we have 3 times 4 times 2. And then there is no other force here except VC. If you take the moment of VC, it will be 0. So you equate it to the bending moment at C, which is minus 4.48. So by that we have only one unknown, VD. If you solve for VD, it gives you this 4.88. Now we have been able to find VA and VD. We will need to find VC, VB, and VC. The next thing is to stand at C and take bending moment to the left hand side. Of course, you can stand at VB and take bending moment to the right hand side. You'll still be able to find VC. But what I did is stand here, take bending moment to the left hand side because I know VA. So the only unknown will be VB. Then I can solve for VB. This is what I did. So I stand at C, take bending moment. You will have the force VA, and this will be clockwise moment, and the perpendicular distance is 11. The next one is 9, anti-clockwise, so it's negative. Perpendicular distance is from here to here, I think is 3. The perpendicular distance is 9. So from here to here is 9. That is why we have this. The next moment is VB. VB will give a clockwise moment. That is why it is plus. Perpendicular distance here is what? Is 5. So you have plus 5. The next one is this 8 kilonewton load. And it's giving you an anti-clockwise. That's why it's minus. The perpendicular distance is 3. So you have this. Remember, you're taking moment from here. So equate it to the moment at D, which is minus 1.448. You will have two unknown, but of course we know our VA. We have calculated VA, so you start with the value of VA here. You will only have one unknown, VB. You make solve for VB, it gives you 9.41. So we now have VA, VB, VD. The only thing we don't have is VC. You can start at B, take moment to the right hand side. You will have two unknown, VD and VC. So you solve, but you know VD. So from there you can find VC. But what we did was to take sum of upward and vertical, sum of vertical moment equals to 0. So by doing that, our VC gives us this 9.85. And so we have been able to find our support reactions, which can help us to draw a shear force diagram. This is a shear force diagram. If you follow the way I did in our example 1, in our phase part 1 of this lesson, you will get it. But let me also point out, when you're drawing the bending moment diagram, look at the bending moment diagram here. You have the two support moment. You have calculated 6.84, 4.48. Remember, the moment here is 0 and the moment here is 0. So you have our moment support moment equation. When you want to superimpose the simply supported moment equation, of course you know this. For this one, we have our the simply supported moment is here. The maximum point is what? 9.6 kilonewton meters. So if you come here, this now means from here to this place is 9.6. Let's go again. It's 9 point, no, okay, it's 12. It's 12. This place is 12. So if you come here, from here to here is 12. But how do we know what is here? What is here is you need to work out this place. So how do we know? This place is 0, this place is 6.84. We cannot do 0 plus 6.84 divided by 2 because it's not at midspan. It's actually at 2 meters from here, somewhere here. From here to here is 2 meters this side. So we are going to use the concept of similar triangle to find this distance. If this is 0, this is 6.85. What is this distance at 2 meters from there? When you find that distance, subtract from 12. What remains is this. So that's how we had this. We come here, we do a similar thing. Remember this simply supported diagram was 9.6. So we now come here. This is 6.84. This is 4.48. But at 2 meter, which is not midspan, 2 meter, we use similar triangle to find the distance from here to here. When you subtract it from 9.6, this is how you will have this place. So what we now have is here. But here, we cannot just use from here to here. We don't know exactly the distance where this maximum. These points are easy because we know the maximum momentum under the point load. But this one, we don't know exactly where the maximum moment. So what we do, like we did in example 1, we write the bending moment equation for this span, which is this. So we write, okay, this is a shear force equation for that span. This is a shear force equation, and this is the bending moment equation for that span. Then you use the concept that at the point of maximum bending moment, shear force is 0. So you will go to shear force equation and equate it to 0 and solve for the unknown x. When I solve it, it gives me 13.37. I'll now take the 13.37 to go and put in this bending moment equation. When I put it, this is what I did. Wherever I see x, we put 13.37 and it gives us 3.96. So that is our bending moment. So we know that the maximum bending moment is 3.96, and we know that it's happening at a distance of 13.37 from this left support. So for us to find this distance is 2 plus 4, that is 6 plus 2, 8 plus 3, 11. So the whole of this distance is 15 meters. So from here to here is 15. If we subtract the 13.37 from 15, we will have from here to here give us 1.63. So we know that our maximum moment occur at the distance 1.63 from the right support, and its the magnitude is 3.96. So with that, we have been able to draw the bending moment diagram for our bending moment diagram and shear force diagram for the beam we were to analyze. So that is it for this side. Let's continue by looking at another example with another separate condition. Okay, I think for this video not to be lengthy, we are going to continue in part 3 of our video. That is it for here. Watch out for part 3 to the continuation of this lesson. Please don't forget to subscribe to this channel so that you'll be getting our video. Thank you very much.